L is IW, but I changes depending on the geometry of the thing that we're dealing with. And so we need to know that. Like there's one for uniform cylindrical grinding wheel. So let's figure that out here. I'm going to go to my handy online resource here. We're getting to the book problems. If I could just sync up with your textbook, which I had the link to at some point, we could just find these a little bit faster. Let's see if this is here. Okay, so the geometry says that this is well, can't find. Okay, so it says the wheel, the I of the wheel here, I is 1/2 mr squared. W, it comes from this. The mass is given and the radius is given, so we're pretty much on our way to finding the correct answer here. So to do that, the I here is 1/2. The mass is 3.2. The radius is 28 centimeters. That's 0.28 squared. That's I. And then W is the 1500 revolutions per minute. 1 revolution is 2 pi radians, and then 1 minute is 60 seconds. Okay. So we get these two numbers, we multiply them together, and hopefully we get something reasonable here. I'll do the calculation as well. We'll see if we come up with the same thing. So I get 19.7 for the
19.74.
19.7. It says 3 digits, so I get 19.7. The units. Let's see. Units are.
This where it gets kind of iffy.
Kilograms meters squared. Kilogram meters squared.
Minus meters squared? All right.
Times meter squared, yeah.
Wait, what? Is it kilograms subtract meters squared?
No, it's times.
Oh, times? Oh, that's what I got wrong. Okay, my bad. Yeah, yep, I'm doing that incorrectly.
Is that correct?
I think that your answer is correct. Oh, enter your answer using, I'm using the wrong stuff. Kilogram. I'm entering it incorrectly. That's my bad. Oh my god. Kilograms times meters squared. I put kilogram times meters squared, but it said it wasn't acceptable for some reason. Enter your answer using units of angular momentum.
Oh yeah, angular momentum is something different. I don't know what it is. Let's see.
Let me check.
You can always check like a previous problem, units of angular momentum, and it's per second. Per second.
Oh, over? Okay.
Yeah, over seconds.
And that's correct.
Okay.
How much torque is it required to stop in 7 seconds?
Yeah, so torque is equal to L over T.
Okay.
And we have L. We have L. We just it's our calculated value from previous problem, and then we divide it by 7. And it's always good to go back to that full calculation there, which is I get 2.81, and then units of torque here is newtons times meters.
2.81 meters times meters. Says the compound is not recognized. What? The unit you have entered is not recognized. Review a list of acceptable units. So I think the answer itself is right. I think it's just the units that I've presented. It's probably an error on my part. Give me a sec.
So it may prefer, so there's kilogram time meter squared over second squared. That'd be another possibility.
Kilogram times meter squared?
Over second squared.
Kilogram over second squared, right?
Kilograms times meter squared over second squared.
Oh, times meter squared over second squared. Okay. Now we got meter squared over second squared. That's correct. All right. On to the next problem. I think it's 8.67 for the next one.
Okay, let's see. Yep, we got that here. Let me see if I can find the textbook that goes along with this, so I can get these solutions a little bit faster.
Go for it.
These keep being part of they're just Chegg Q&A that people answer, but this is from a textbook, and it would go a lot faster if we could find them. We had it here. I thought I had saved this. Let me just go back and look at my history here. Do you remember last time we did a physics lesson? I know it's been a while.
I think it was like a couple weeks ago.
If you can give me the date,
Before we're gonna break.
I'm searching here for.
I think it was Wednesday. Was it last Wednesday?
I'm seeing some stuff. Yeah, I'm seeing some stuff last Wednesday. Let me see if I open that one up. Yeah, there it is. Let me see. Okay, this might go a lot faster if I can find it. Plus, the solutions have pictures, which really help going through this most of the time. This one doesn't. Okay. All right. So the person stands at the center of a rotating merry-go-round. So they're standing here right in the center, and then they walk towards the edge. So at a later time, they're here at the edge, and it says they want the angular velocity when the person reaches the edge. So there's this thing called conservation of angular momentum, which is I initial omega initial equals I final omega final. So the person has an initial momentum, which they give you. They give you this I0 is 860. Okay. You can calculate W0, that's V0 over R. Mm-hmm. And they tell you that it rotates with angular velocity 0.85. So we've got a ton of these. We've got a bunch of these values that really helps here. Us do this. So the
right.
Now I'm just looking through what else we got. So the omega final, W final, is I initial W initial over I final. Okay. So I initial is the 860. And the omega initial is the 0.85. that's given in the problem. Okay. Now the final, this is where it gets a little bit unclear for me, other than just giving you the solution. So there's it's the from the previous lesson we did, it's the angular momentum of the center plus the one at the end. It's this parallel axis theorem that you might, so it ends up being this I initial plus m r squared, because it's a they assume that it's a I think it's a disk there. So this is because it's a disk, and that's the one that it started with. So your initial is 860. Your mass is the mass of this person, which is given as 860. And then the radius is 3.2 squared. So this calculation is 860 over this, 860 plus this number. Wait a second. The mass is 79. Sorry, I got the wrong mass. Mass is 79. Let's look at the wrong number. Okay, so to summarize, it's 860 times 0.85 over 860 plus 79 times 3.2 squared. I'm going to my calculator, 860 times 0.85 divided by 860 plus 79 times 3.2 squared. 0. How many decimal places? Let's see, does that for 3? 0.438. 0.438, and it does match the units of omega initial radians per second. So give that a try. See if that's correct.
Initial radians per second. So
Yep.
0.438. Typing it in right now. That is correct.
Okay, so the next part of this is asking for some energy, I guess. Yes, yeah. So it's kinetic energy. So the kinetic energies here, it's pretty straightforward. Like this is a nice calculation. The kinetic energy is 1/2 I W squared. Okay, so like for the initial, they give you I. They tell you I is 860, and W they give you that was the 0.85 squared. So that's really straightforward. That's just putting the numbers in that are given. The final kinetic energy is much harder. But let's get this number first before we move on. So it's 1/2 times 860 times 0.85 squared, and that is 311 joules. Okay, now the kinetic energy after, at a later time, it's also this 1/2 IW squared, but just like we did in this previous calculation, it's got a couple components to it. It's the I initial plus the MR squared W squared.
All right.
Okay, so now you have all these values. The initial was 860. The mass is just known, that was 79. The radius was 3.2 squared. Okay. W is the value you calculated from the first problem. So you want to use that unrounded omega, which was 0.438 with some other stuff there. And that gives you your second energy. So what I got to do is go back, save that value for W. So that's 1/2 times 860 plus 79 times 3.2 squared times W. W squared. So that's 160 joules, because that number's squared. Okay. Give that a, so the answer is looking for both of those in the box there. It looks like it wants both of those numbers. Oh, I don't have it up. It wants 311, 160.
310, 1160, correct?
The numbers
Oh
are
wait,
here.
no, never mind. 160. I was blind. I'm blind.
Yeah.
All right, there we go. Wait, so your submission doesn't have the correct number of answers. Oh wait, no, there are 2 in there. Yeah, I'm blind. All right, 160. There we go. Do you mind if we work on some math real fast?
Sure, whatever you'd like. It's your time, so we'll transition whatever you want to work on.
Sounds great. I'm going to share a document with you. Learn a little bit more about some of my lessons. All right, there we go. Share it with you, your students. Send. All right, there we go. This is going to be some graphing.
Okay. All right, let's see. Okay, it looks like it is there. I'm gonna open that up and take a look at it. So we got a test review coming up here. Okay, so let's see here. Okay, so we got some graphing, really some ugly graphs that your instructor put here,
Yeah.
all stretched out. Okay.
Yeah, it's kind of one of those things where you can just kind of like type in the Desmos and be done with it.
That's right. That's right. But you have to do this by hand. Then there's some things that need to go into it. So the amplitude is the number that's out in front, which happens to be 1. It's the absolute value of that number. So it happens to be 1 there.
1. All right.
The period is 2 pi over b. Period is 2 pi over b. What is b? B is the number in front of x.
Okay.
So the number in front of x is
3, right?
So it's 2 pi over 3. That's your period.
Oh. I jumped ahead.
All right. This is where it gets a little. This is where I'm going to differ in what your instructors might say to do. This one has a really challenging period to actually graph. I'm going to arbitrarily call this, well, you see, what you're going to want to do is go 1 pi over 3, 2 pi over 3, 3 pi over 3. That would be, I guess, somewhat reasonable. So that's 2 pi over 3. Okay. Problem is we're going to have to fit our graph into this really small space. So there's 5 points when you're graphing a sine wave and 5 points when you're graphing a cosine wave. So the sine wave goes up high, comes down, keeps going down, and comes back up. So there's 1, 2, 3, 4, 5 points. And you can see here, you find the midpoint. There's the midpoint, and then you go up a little, you go down a little. So this looks like it's got this right in here, this little small piece. It's kind of scrunched into this little area.
Yeah.
You can choose whatever you want for your units. Like you could just as well have said, there's 2 pi over 3, Matthew, or whatever, like wherever you want. It's got to have this shape though, and the instructor's looking for the period. So usually you have to go back another period. So this has the same shape as this, but it's currently, you just have to copy it over. So it starts high, comes low, comes back up.
All right.
Like that. And so that's how you do that for this graph here. So that's really all there is to say about that one. If you need more explanation, you can provide that, but I'm ready to move on to number 2, unless you
I'm fine with moving on to number 2.
Okay. Looks to me like okay, there it is. Question 3 was on the bottom there. All right. Okay, so the amplitude is the absolute value of the number in front. So it has an amplitude of 4. The period is 2 pi over the number in front of x, which is 2. So that 2 comes from there. So that's just pi. So the way that I would tell you is to ignore this, but go out sort of like midway over here and call
Mhm.
that pi.
Yeah.
Then you cut it in half, and that's pi over 2. Okay. And then again, the sine wave, like what sine does is it, and then you actually need these 2 other places. So you need 5 places as you're starting here. Sine always starts high, comes down, goes low, and comes back up. It always has that shape. Okay, but the thing that affects it now is this amplitude. The amplitude pulls it up and down. So instead of it going to 1 here, it goes up to 2, 3, it goes up to 4. Instead of this being at -1, it goes down to -4. So this has the effect of pulling it up and down like that. So that's what the 4 does. But it's not 4, it's -4. So what that does is it actually flips everything. So this comes down this direction and looks like this. So the completed graph here, I actually guess I really do need to change colors here. The completed graph is going down this direction, starting down, coming up, and going down, like that. You've got Desmos. I don't know if you're allowed to use it during an exam, but I mean, it's way better than trying to do this by hand.
Yeah, free money.
So copying this over, I'm copying this way is one way to look at it. Comes down here, comes down here, comes down here. So it has this shape. It's nice shape to it, and it goes on forever, repeats forever. All right, number 3. So we got a cosine. Structure throws it. Oh, you know what? I graphed the first one. I graphed this first one as a sine, not a cosine.
Oh,
That does actually change this quite a bit. So forgive me here for that. What it does is it changes what the parent function is. I didn't even catch that. So oops, that's still red. So the way cosine looks is you still have to go out, you still need those 5 points. But what it does is it starts high, goes low, reaches a minimum and comes back up. 1, 2, 3, 4, 5 points. So we're still doing the same thing. We've got this 2 pi over 3 right in the middle, right in the middle, right in the middle. So it comes down and comes back up like that. And then you have the same behavior over here. So it starts, it comes down like that.
all right. I know I'm kind of skipping all over the place, but could we also look at another test review?
Whatever you want.
All right.
It's totally up your time. You direct me. I don't have to spend any more time on this if you don't want me to.
I'm
In fact,
gonna.
I wouldn't. You can sit there and graph all these and find the information you need.
All right, I'm gonna pull up your. What is it? The email. I don't know why I just had mini brain fart. Here we go. Reply. I'm gonna send you a screenshot of this. So it's like one of those test review games.
Okay.
It's not really a game; it's for a grade. So I wanted to
Yeah.
look at it.
How fun.
Yeah, that's always my favorite now. Did load in on your
Yep,
end?
I got it there. So we got a bunch of these screenshots. Or you just did one at a time here?
Yeah, I just kind of wanted to do one at a time.
Okay. So the period. I mean, we can do this almost visual. I'll snip it in, but the answer is peak to peak or valley to valley, and
All right.
sometimes that's easy to distinguish. Sometimes, like in this one, it's a little bit harder because the peaks aren't really given. Like that peak and that peak aren't given, so you have to go to the same place. Like that one's at a nice point. That one's a nice point there. So where am I when I get back to it? Ooh, um, that doesn't help either. Um, wow, this is horrible. So,
Easily done, huh?
well, it's not helpful the way they've got this. Like the units here, like this is pi. This is more than pi, or pi over 2. Each width here is pi over 2.
Mm-hmm.
This peak to peak is a little more than pi over 2. So just based on these answers, is probably 3 pi over 4. There's actually not enough information to they haven't given you enough,
Determine.
like correctly. You can infer this. It's definitely not that one. It's not that one. It's not that one. It might be the pi over 2, but the way it's kind of drawn. But I think to me, it looks like this peak to peak is a little higher than this one, this width here.
This next one says, what is the period? How do we calculate period again?
Well, it's peak to peak. It's whatever the distance is from peak to peak, or valley to valley, or a point to at the same point. You're just trying to find the width there.
Yeah. Well, what if I'm looking for like an equation where it's like like for this next one, it says y equals 4 cosine 5x. How do I calculate that?
Is this what you said?
4 cosine 5x. You got
Okay.
it correct.
The period is 2 pi over b. B is the number in front of x.
Which is
So
5
the period is 2 pi over 5.
All right. The blank represents half the distance between the max and the min of a sine or cosine graph. I might have to. Do you want me to?
It's usually the center line, which is the vertical shift, the value of d. I don't know what options you're given, but that's what it kind of sounded like.
It gives me frequency, amplitude, period, and extreme values.
Yeah, probably need a picture. So
Okay, yeah,
somehow
I'm gonna send you that.
the
I
words
was,
aren't
yeah,
making sense here. But are you only able to go one at a time on these?
yeah. That's kind of how this one goes. It's a little bit of a pain, but we can get through it. I sent another reply to your email.
Okay. Half the distance between the max and min. Oh, okay. It's amazing how seeing it helps. Let me just snip this in. I'll draw a picture to explain. So let's just say this is a sine wave. It goes up and down and back up. Okay, or
Yeah.
whatever. There's this to this. Okay, that's what it's saying. But it's half the distance. So half the distance. Well, the total distance is this right here that I've drawn. Half of it is this much, which is the amplitude. The amplitude tells you how far up you're going from the center line.
Okay. Is that the whole answer for this one?
Yep.
Oh. I was waiting for something else. I
Nope,
guess.
that's it. There's a couple of different ones of these, like there's the vertical shift.
This one's pretty weird looking. I'll send it to you. All right, sent another screenshot to you.
All right, waiting. All right, you said you sent it. Yep, there it is.
I sure did.
Okay, like the way I would tell you to do this, if I wasn't here, is I would use Desmos to do it.
Mm-hmm.
We can do it by hand, of course, but what they've given you almost an incomplete graph. They really haven't shown you enough, but there's a graph here that goes between these peaks and valleys.
Okay.
And so what does this look like? If it starts high, goes low, and comes up, that's a cosine. Okay. I mean, that's kind of a important baseline thing here. So these U shapes here are 1 over cosine, which is secant.
Okay.
So we got it's no because those are the wrong graphs. So now is it secant?
I
or is it
think it
two
would be
secant?
2 secant because it's going by 2, right? Like if you
It's
look at
because
the
of
height
that's
and
two.
below.
Yeah, that's why it's two secant.
Okay, that's very clear. Thank you. Oh my, these are very interesting to look at. Handing this one your way. There we go. Cancel that. Send. There. Sent as a PNG. How do you know when it's a sine versus a cosine or a secant or whatever?
Well, there's this, the sign always looks like this: starts high, goes low, comes back up. I keep drawing this, not so great, but it does that. And then cosine starts high, comes low, and comes back up.
Oh,
Okay, that's there's a huge difference between the sine and cosine. One starts here and goes high, the other one starts high and goes low. That's how you have to start out by understanding. And then the secant, cosecant are based on knowing that. So the one you're looking at here is definitely a sine function. So that means the only one you can get rid of right away is the cosine. What is the how high does the graph go and how low does it go?
it seems to go high up to 3 and down to negative
Right.
3. So I would
So
think it'd be 3, right?
yeah, so the amplitude is 3 in this case, which means that A is the only possible answer.
What would the other one look like with the 1/3 x?
It's pulled out, so it would go to 6 pi on the right. It would take 6 pi to get a full period.
Oh, would it be
So,
like super tiny, like really
no,
thin?
so if this is a sine, the 1/3 pi would just take a third as long to get out there. It would look like that.
Oh, okay. I see what you mean.
I exaggerated that, but that's that kind of thing. All right, is there another one coming
Yes,
up?
I am
Okay,
sending that your way.
we'll just keep having to do this back and forth thing. Um,
This is kind of one of the parts I don't like about online school. It kind of takes out the interactive part of it.
yeah. Do you want me to log in so we can do this a little faster, or up
I'm
to you?
already logged in on my
Okay.
side, so it doesn't
All right.
work.
All right.
What is the equation of the graph?
Okay, there it is. And you said, okay, what's the equation of the graph? All right.
It looks like it's a sine because it goes
It is
down, goes
definitely a
up.
sine. So now you gotta find the period, and this is a good one to do it with. That first question didn't have much
Is
help
this
for us.
is this the red one, 2 sine x?
Possibly, but what I want to make sure is you understand, you see here is if you go peak to peak, okay, that's 5 pi over 2 minus pi over 2. That's 2 pi. That's your period.
Yeah.
That's what I meant by peak to peak. Now, the period is equal to 2 pi over b. Okay,
Okay.
so what we have now is since the period is 2 pi, if this equals 2 pi over b, well, b must be 1, because the only way you get back 2 pi is if b is 1. So that means, yeah, it's got to be sine with a 1 in front. So um, it now we consider the amplitude. So this is an amplitude of 2. Well, how high up does the graph go? It goes up 2. So that's why, yeah, D is correct.
Already sent. There we go. Right, an equation for this graph. This looks like an inverse. So let's see, that goes down, then goes high, goes down and goes high as sine, or no, cosine,
Looks
and
like
then
it's a reciprocal of cosine. So that means it's a
secant.
secant. And then the next thing you can say, well, how high up does it go or down does it go? It goes to 3.
Mhm.
So it's a 3 secant. And then the last part is whether it's an x or
Or
a
2x.
2x. So what's the distance between two mins or two maxes? Like the humps there. Like
The
you see when
two
it
mins or two maxes. Let's see. It's a difference of, there's that, just pi.
pi. That's right. So your period is pi. So which of the
Will it
two
just
on
be
the right?
2? Will it be
Yes,
2x?
it's b2x. Yep.
Oh, so it'll be purple right here?
Yes, it's purple.
All right. Okay, that makes a lot of sense. Attaching it. Sending that. Should be sent. There we go.
What is the period? We just did one like this. Is this a repeat?
I guess so.
So it like valley to valley is a little, or peak to peak is more than one of those rectangles, and each rectangle is pi over 2. So it must be 3 pi over 4.
Just sent the next one.
Okay.
So it goes up 3, 3. Is cosine when it goes down and goes up?
Cosine starts high and comes down.
Is it,
And
is it just B right here?
still, yeah, that just came in. I mean, it's about a 30-second process. So this one is a cosine, and then it's got a 3 in front because of the fact that it goes up to 3. So it looks like it's that aqua teal color, the second one in from the left.
All right, just send the second one. How do you find amplitude again?
Of the equation or the graph?
Of the equation.
It's the absolute value of the number out in front.
This one looks like it's just 2.
All right, I just got it here. Yeah, this it's just 2. Yep.
Perfect. All right. Keep trying the next one. All right, get this. Attaching that. All right. This looks all right. So this one goes up and goes down. If it goes up and goes down, it's sine, right?
Yes.
So then cosecant is the reciprocal, and it goes all the way up
But this one
to.
is it starts high and goes low when you graph
Oh yeah, the 0. I see what you mean. So
so
it's secant.
it's a secant, and then is it, is it,
It doesn't go 2, so it's just
yeah, it's
just
just the,
B right here, right?
yep.
All right. All right. Wait, the period is just 2 pi over B, right?
For sine and cosine, secant and cosecant. For tangent and cotangent, it's something different.
All right, so we can just completely ignore that one now. All right, send you another one. This one goes up and goes down. So that's sine.
That's right. That's sine.
All right, so then it's the reciprocal of sine, which is what is that?
Cosecant.
Cosecant. Okay. So cos. This one looks like it's just cosecant, but I'm not 100% sure.
Still waiting for something to come in.
There we go. It just sent.
Okay.
That one took a little bit longer for some reason.
Yeah, this one's a little harder because it's shifted out to the right, but you could still say that it started. Well, there's actually a couple of possibilities here. Um, oh, well, this one actually is a tangent or a cotangent. So the way you decide that is you have. I mean, you can obviously just graph it in Desmos, but um, if you look at a graph of tangent x, tangent is sine over cosine. And
Okay.
it's undefined when the bottom is equal to 0. Well, where is cosine equal to 0? Well, it's equal to 0 at, I mean, you at pi over 2 and 3 pi over 2. Okay,
Okay.
this is cosine. So that means that the function is undefined there. So does this one have a vertical asymptote at pi over 2 or 3 pi over 2? No. Cotangent of x is cosine x over sine x. Where is sine of x equal to 0? Well, it's equal to 0 at 0. Okay, and then back down here at pi. So that's going to have a vertical asymptote at those 2 points. And that's what you're seeing here. That's what you're seeing
So
in this
looking for that
picture.
cotangent here.
Yes, this is cotangent. And they look really similar, so it's very easy to not know the difference between them. But it comes down to where these vertical asymptotes are.
How do you know if it's sine or cosine again? Sine goes up and goes down.
Yeah, sine starts in the middle and goes up. Cosine starts high and goes low. This is the graph of cosine. This is the graph of sine.
All right, we're done.
Great.
All right. Can we do one more physics problem?
We can try. Let's see. I got to get back to that.
Let me see if there's one that's just a one problem kind of thing. 8.3 is just one thing.
8
Determine
point.
the inertia of 15.0 kilogram sphere radius. Wait, what?
Okay, so this one, let me snip it in. Okay, question 30. Okay, so the moment of inertia I is based on the geometry. Here it's well, that's weird. I is 2/5 mr squared, and that's because it's a sphere. That's like a note. You have to know that to be able to do this problem. So that's 2/5. The mass is 15, and the radius is 0.654 squared.
Okay.
So the key here is knowing your formulas. That your instructor has an obligation to give these to you so that you know which ones to use. This one, it doesn't say how many, so we'll say 3 significant figures, 2.57, and then that's already got the units there for you.
That's correct. All right, let me see if there's another one that's just one problem. 8.32 is just one problem. This is a part A.
Okay, let's see. Assuming I got a merry-go-round accelerates from rest, calculate the net torque. Okay. So the net torque is like I alpha, and we'll see. This one's got a few intermediate calculations, I believe. So let's see if we can get this in. Okay, so the net torque is equal to I alpha, and the I is again kind of that key thing here that you got to be able to know that you got to have some idea of what the geometry is. The because it's a disk, it does say uniform disk. I is equal to 1/2 mr squared. So you have these numbers. You have that the mass is the 3.2 times 10 to the fourth kilograms, and the radius is 8 squared. So you can get the inertia. Alpha, though, you don't have, but you can calculate. Alpha is the change in angular momentum, the omega final minus omega initial over time. Since it started from rest, the omega initial is 0. So the omega final is 0.73 over 32. So there are your two values. You have to take that value and multiply it by this one on the right. You end up getting a number. It's kind of large, but it says 2 significant figures, so might have to do it in in SI units. And it's a Newton times meter, but last time we had an issue with this. We had a kilogram meters squared per second squared. It was like one or the other. I don't know what it'll take this time here. So let's get that calculated. I is 1/2 times 3.2 times 10 to the fourth times 8 squared. And then the alpha is 0.73 over 32. So it ends up being 23360, but that's not to 2 decimal places. So that's really like a 2.3 times 10 to the third kilograms times meters squared per second squared. I'm sorry, 10 to the fourth here.
2.3 times 10 to the fourth kilogram. And that is correct.
All right, let's stop here. Thanks again for scheduling, and be happy to help you again next time.
Appreciate your time, Matthew.
Okay.
Have a nice night. Appreciate it.
You too. Bye now.